Okay, so what we're going to talk about is basis, and it's sort of pulling some things together. So a basis, say you can be a basis for any sort of set of vectors, but if we're talking about for R3 first, then it must both span R3 and be independent. So being independent, basically there's no extra vectors, and I'll talk about what that means. And span means that linear combinations of those vectors that form the basis can give any other vector in R3. So linear combos will give other vectors in R3. Okay, so you can do that. Okay, so I've got two examples here. So let's look at the first one. So the idea would be that you would first set them up as an augmented matrix for the homogeneous system. So that means we would put them into a matrix. And the homogeneous system means that we put zeros on the other end, and then we reduce. So we saw this before, and we augmented them instead with a general vector in R3. If we were asked for the exact span, what type of vectors this spans, then we would want to do that. But if we're just looking for if it's a basis, we can just put zeros and make things a little bit easier. So let's go ahead and row reduce this. So we've got a 1 in row 2. We always take the pivot, that 1, multiply it by -1 and add row 2. So we'll do that. And then at the same time, this is a +2. I would need the 1 to be a -2. All right, so let's go ahead and do these steps. I'm leaving that first row alone. And then my second one. Okay, 0, -3, 2, 0. And then this one, -2 row 1, so -2, -6, 2, 0, and add row 3. Okay, I can actually stop at this point because I do notice right now that my row 2 and row 3 are the same. And so that means I am going to get some free variables here. And this will not span all of R3. But let's continue on just to show you. But I do notice right now that this, so let's leave this pivot as a -3 for a minute, because that will easily get rid of this +3 if I just take row 2 and add row 3. And the same thing here, row 3, I could do negative row 2 plus row 3. Instead of making this into a 1 first, we'll do the 1 after. And so I would do that by dividing by 3, but I'll just do that step last. So first I will add these two. Then I will subtract them here. So negative row 2 plus row 3, 0, and 0. And I get all zeros here because these two rows were the same. So when I subtract them, of course, we get zeros. And then let's just divide this one by 1 while we're at it. Okay, so this is fully reduced. I can see that I've got a row of zeros here, which because there are the right number of vectors to span R3, you need 3 vectors. But I do notice that Z will be a free variable because there is no lead 1. There's a lead 1 for the X, there's a lead 1 for the Y, but the Z has no lead 1 in this position. And so we would say that's free for T. And so to span for 3 vectors, to span R3, there needs to be a lead 1 in each row. So there's a lead 1 in row 1, and there's a lead 1 in row 2, but there is no lead 1 in row 3. And so these three vectors do not span R3. So right now I can see that they do not form a basis, but let's talk about independence first before I move on to the second example. And so for three vectors to be independent, the only solution must be x equals 0, y equals 0, and z equals 0, i.e., there are no free variables. And so for this instance, there are free variables. So the solution is not going to be only that. And in fact, the solution to this system, we would say, is x plus z equals 0. That's from the first row. And the second row, I get y minus 2/3 z equals 0. And I know I'm going to let z equal t. So my solution to this is x equals minus t, y equals 2/3 t, and z equals t. So definitely this has more than just one solution. It's dependent. And if you wanted the dependence relation, you would just plug a number in for t. Let's say we let t equal 1, then we would have -1 times the first vector plus 2/3 times the second vector plus 1 times the third vector is equal to 0, 0, 0. And I just need to write the vectors in there. And the vectors were 1, 1, 2, 3, 0, 3, and -1, 1, 0. That's just from the original question up here. Okay, so the first one does not form a basis. So let's see one that does form a basis. Okay, so this one, if we put this into an augmented matrix, and then we row reduce. So I made these numbers up, so hopefully they will work. We've got a 1 here. We already have a 0, so that's good. Row 3, that's a 1, so we need -1 row 1 plus row 3. So this will give me 0, 3, 0, 3, 2, 0. Now I've already got a 1 here and a 0, that's good. So in row 3, that's a 3, so go -3, row 2 plus row 3, plus row 3, and I can see right now that it's going to work because, and just like the last one, I could tell that it wasn't going to work, but this one I can tell it will work because we've got a lead 1 here, we've got a lead 1 here, and now we are going to have a lead 1 here. Just if I divide by -1. I could also make these into zeros if I wanted to, but it's not necessary. Because I already know that there are no free variables. So if I continue on, I get this. So the solution is x equals 0, y equals 0, and z equals 0. So that means that is independent. There are no free variables. There is a lead 1 in each row. So these three vectors span R3. That means that we can get any vector in R3 if we make a linear combination. So for example, if I took these vectors and I made a linear combination with them, and I put any vector at all over here, so I choose like an x, y, and a z, it will always have a solution. And so that's what it means when it spans R3. The span is like sort of like a fan when you're opening up. You can get any vector at all from these three vectors. So that spans all of R3. So no matter what I choose, if I put 1, 2, 3 in and I solve, I row reduce, I'll get a solution. If I put 100, 1/2, and -5 in, it doesn't matter what values I choose, I will always be able to get a solution using these three vectors. And that's what it means by they form a basis for R3. Now the standard basis are these vectors, which we also say is that I, J, K, I, J, K are the standard basis vectors for R3. They both span R3 and are independent. So that's the standard basis, but there are lots of other bases. And a basis, again, is like three vectors. If it's R3, it has to be three vectors. And they are both, they span R3 and are independent. So what would not be is if they had the wrong number of vectors. So if you had 4 vectors in R3, they might span R3 when you reduce it, but there will always be a free variable. So would be dependent and not form a basis. So for instance, if I took any 4 vectors and I augment it, I'm not going to go through and row reduce this, but you could get, they might span R3 because you could have a lead 1 in each row, but you can only have 3 lead 1s at most. Like at most, you would have a lead 1 here, here, and here. And this 4th row will have to be a free variable. You can't get another lead 1 because there's not a 4th row. So this will never form a basis. Now, what if we had 2 vectors in R3? This also won't form a basis. Let's just look at what this looks like. You can have a lead 1 here and you can have a lead 1 here, but there's no, right, wherever you have a lead 1, you always put zeros above and below. So there, you can't have a lead 1 here because there's not another column to make a lead 1 with. So this can never span R3 because to span R3 you would need a lead 1 in each row. This may or may not be independent That depends if there are two lead variables or not, but it can never span R3, so it can't be a basis. So 2 vectors can never span R3. 4 vectors would be dependent, so they can't be dependent. 3 vectors may work if when you row reduce it, you get the identity here. One's down the diagonal, zeros everywhere else. That would be a basis. But when you row reduce it and you do not get the identity here, then it does not span R3. And if it does have the right number of vectors, then it would both not span R3 and it would always be dependent, because that means we had a free variable if we weren't able to get a 1 there. Okay, so good luck with the test.